Hey guys, so today I want to talk to you about how you know a reaction is going to happen. Let's say you throw a couple of things into a beaker and you want to see if they react. Well, how do I know if something's going to react? There's kind of some rules here. It's based on what type of reaction we're dealing with. Okay, so if you try to do a reaction, is it going to happen? Will they actually react, or will they just sit there and do nothing? All right. First off, the type of reaction, we're going to go type by type here, starting with synthesis. With synthesis, if the compound exists, okay, that you're creating, because you take an element, another element, you make a compound out of them, then that synthesis reaction to create it is probably going to happen. Okay, so if the compound exists, then the elements coming together and reacting to make that compound probably going to happen. So if you get both of those compounds in a container and somehow get them to react, makes the compound. It might take heat. It might take pressure. It might take some other things like electricity. I don't know. There's lots of different things that you can do to get two elements to actually merge and make a compound. And if those elements will, in fact, make that compound, then you can probably find a way to do it. Okay, so in other words, synthesis is always going to happen. Whenever you come across a synthesis reaction that I give you, it's going to happen. Okay? Decomposition. Compounds, if they are an existing compound, they can be broken apart into their elements, either by heat or electricity or acid or something else. There are lots of methods that actually can break compounds apart. Again, it depends on the compound, what you might want to use to do it, but decompositions can basically always happen. It may be difficult to get it to break into its elements, but it is possible to break pretty much anything into its elements. This is actually how we discovered a lot of elements. We took compounds. We found ways, experimenting, to break it into their elements, and then we discovered the elements. Okay, so decomposition can also always happen. Anytime I give you a decomposition reaction, yeah, there's a way you can make that happen somehow. Okay? Combustion. Combustion involves hydrocarbons, and hydrocarbons, one of their properties is that they're flammable. Hydrocarbons always burn. So in order to be combustion, it has to have a hydrocarbon, and a hydrocarbon is always flammable. Therefore, combustion always happens, as long as you have the oxygen and the heat to actually start the fire. Okay, fire takes three things. It takes fuel, oxygen, and heat, and once you have all three, it's going to burn. Okay, so combustion's always going to happen every time I give it to you, as long as it's a hydrocarbon, and of course there's oxygen there, it's going to happen. Okay, so these three reactions, synthesis, decomposition, and combustion, you don't need to worry about determining if they happen or not. If I give you one of those three, it happens. Okay, you have to find the products for them. All right, those happen. Any of those three types. The other two, single replacement and double replacement, though, you have to determine if they happen, because they don't always happen. So I might give you a reaction, and it might not be a possible reaction, in which case, you don't have to write the products for them. Okay, but if it does happen, then you do have to write the products for it, because it does happen. All right, so let's start with single replacement. How can you tell if a single replacement reaction happens? There's something called the activity series. Okay, now I gave this to you in your lab supplies kit. Okay, it's on this green piece of cardboard, so if you pull this out, you're going to need this for these notes here. The activity series is some stuff on the back that we're going to use later about bond enthalpies and equations. Flip to this side, it has solubility rules for ionic compounds, and then at the bottom of it, it says activity series of the elements. Okay, so what the activity series is basically a list of metallic elements in a specific order. And this order describes how reactive they are. Okay? Metals that are at the top of the activity series, metals way over on the left, on the one I gave you, are more reactive, and they will always replace less reactive metals that are below them if they come across them in a compound. Right? For example, if you have something like lithium, which is the most reactive element in the activity series here, if you have the element lithium and you mix it with any of the other elements, okay, that are on this activity series in a compound, the lithium will replace it. Okay, the lithium will replace a part of that. The single replacement reaction will happen. Okay, however, if you have a metal that's at the bottom, that's not as reactive, okay, it will not replace anything above it. All right, so let me show you a few examples here. Okay, so I've got 3 examples up right now. So we've got aluminum reacting with copper to chloride. Okay, aluminum with copper to chloride. Now, aluminum here is a metal. So in this compound, this is a metal as well. So the aluminum is going to replace the copper. Okay, I want to determine if this reaction is going to happen. So I'm going to look at my activity series here. And this is the one I gave you guys for reference. It's just a reference sheet on this green thing. Aluminum is located right here. Okay, so what I want to do is, now that I found aluminum, find copper and compare it. So look on down here, and copper, symbol is Cu, it's right here. Right, so this is the more reactive side, and this is the less reactive side. So aluminum is more reactive than copper, which means that aluminum will replace copper if aluminum comes across a compound that has copper in it. Okay, which it does here, which means this reaction happens. So the aluminum is going to replace the copper and kick it off. We're going to have aluminum now paired with the chlorine. Okay, and then the copper got kicked off. Now I got to look up charges here. So the aluminum is +3, copper is -1, or chlorine, sorry. So this is AlCl3. Okay, and then after this, I would just have to balance it. So this one balances 2, 3, 2, 3. Okay, this reaction does happen. This is what would happen. Okay, you have to write the products and balance it. Now let's take a look at the next one. Nickel, the element, reacting with the compound sodium chloride. Okay, does this reaction happen? Well, nickel is a metal. Sodium is the metal in the compound, so we have to compare. Does nickel replace sodium? Okay, so here's my activity series again. Find nickel here. Let me see, where is it? It is right here. Okay, so here's nickel. And now I'm going to find sodium. And sodium is over here, above it. So that means that nickel cannot replace sodium. Sodium could replace nickel, but nickel cannot replace sodium. Essentially, these reactions are sort of a one-way street. One can replace the other, but then it can't go in reverse. Okay? So the nickel cannot replace the sodium. All right? This reaction will not happen. There would be no reaction if you mixed these two substances together. All right? Now, when you come across a reaction that doesn't happen, all you got to do is write no reaction. You don't have to figure out the products. You don't have to balance them. Nothing more. This problem is done. All right? Let's try the next one. Lithium and zinc carbonate. Okay? Lithium and zinc carbonate. So, lithium is a metal. Zinc carbonate. The zinc is the metal. So I'm going to compare lithium and zinc on here. So here is lithium, and lithium is the most reactive. Basically, lithium can replace everything. Okay? Zinc, if you want to find it here, is actually right here. So yes, lithium higher than zinc on this reactive scale here. So lithium can replace zinc. So this reaction does actually happen, which means that the lithium is going to replace the zinc, and we're going to be left with lithium paired with the carbonate. And the zinc gets kicked off. Okay? Looking up charges here, lithium is a +1, carbonate is a -2. So that means that we are going to have 2 of these lithiums, okay, in this compound. Balancing this is going to have to balance 2 lithiums and then 1 of everything else. All right? Push this up here. I got another example. This one is iodine reacting with sodium chloride. Okay? Iodine. Now, iodine is a non-metal. Okay? This here is a metal, so chlorine is the non-metal. Right? So the iodine is going to not replace the sodium, it's going to replace the chlorine in this case. Remember, it replaces whatever it's most similar to. Okay? So the iodine replaces the chlorine. Let's go ahead and take a look at this activity series here. So, on this activity series, find iodine. It is nowhere to be found. Find chlorine. it is nowhere to be found. And the reason why is because this whole list is metals. So when we go to this, all of these are metals replacing metals, whereas this right here is a non-metal replacing a non-metal. All right. So what I have down here underneath this, there's more metals here. There's a short list, which is non-metals. It's just the halogens. Okay. So this list down here is the non-metal version of this list. Okay, you're going to use it occasionally, but it's non-metal. So here's iodine, here's chlorine. So chlorine's above iodine. Iodine's below chlorine. So chlorine can replace iodine. Iodine cannot replace chlorine. All right, same idea. It's still in the same direction. Okay, so iodine cannot replace chlorine, which means this is no reaction. Doesn't happen. Okay. Now, there's another type of single replacement reaction, and all three of these involve water. Okay. So a single replacement reaction involving water, first off, it is a single replacement reaction. The aluminum is going to replace a part of this compound. The calcium is going to replace a part of this compound, making it single replacement. But the ones with water are a little different. Okay, so I want to show you on this chart how to deal with water. So this is aluminum in water. So what I'm going to do is find aluminum. It's located right here. And I want you guys to pay attention to the information written in these sections here. Okay, so all of these elements, lithium, rubidium, potassium, barium, strontium, calcium, sodium, all the way to this line, they can react with water, and they're going to form a metal hydroxide. All right? And then everything here, magnesium all the way through cadmium, they can react with water vapor, meaning hot, gaseous water only. So if it's cold water, it will not react. All right? And it will form a metal oxide. That's the metal, whatever metal it is, with oxygen. All right? These ones here will not react with water. These ones here will not react with water, but these ones also do react with oxygen to form a metal oxide, the metal plus oxygen. And then these three pretty much don't react with water or oxygen or anything else. They're very unreactive. Okay? So our aluminum falls right in here. It says it can react with water vapor, meaning it has to be hot. So if this reaction is hot, it will react with the water. If the reaction is cold, liquid cold water, it will not do this reaction. Okay? So you can have aluminum sitting in a glass of water and it will be fine. It won't react. However, if you have aluminum and it's boiling and having water vapor around it, it will react and form the metal oxide. It will form aluminum oxide. That's what that means. Okay? If you mix one of these, it's going to form the metal hydroxide, which is, like, for example, potassium hydroxide or barium hydroxide is what it would form. And it always reacts with water, by the way. This, only if it's hot. So aluminum, if it's hot, so I'm just going to put that here. It's got to be hot. Okay, so if the description of the reaction says that it's hot, this will happen. So since we're going to say it happens, it's going to form the metal oxide, so aluminum oxide. So it's going to pair with the oxygen, aluminum oxide, A and L. And then what's it kicking off? It's kicking off this hydrogen, kicking off H2. Okay, that's the element hydrogen. Now I'm going to look up charges on the aluminum and oxygen, +3 and -2. So the ratio here is 2 of these and 3 of those. Okay, so we've got my 2 products now. This is one of the diatomic elements. And now I'm going to balance it. I am going to need 2 of these, 3 of these, 1 of these, and 3 of those. Okay? All right, so calcium with water this time. Let's check this one out. Calcium right here. And it can always react with water, no questions asked, but it's going to form a metal hydroxide. It's going to form calcium hydroxide. So I'm going to go back to this here. We've got our calcium. It's going to pair with this, and it's basically going to react with half of this. I'm going to rewrite this as HOH. All right? So it's going to react with the hydroxide part of it. And so it's going to pair up calcium with that hydroxide, OH part. Okay? So we're going to get calcium paired with hydroxide. It's still a single replacement. All right, and kind of got ahead of myself here. This is a positive 2 and it's a negative 1. So pairing them up, you're going to have 2 of the hydroxides. And then hydrogen gets kicked off, and it's diatomic, so H2. Okay, I know we're only kicking off 1, but because when you kick off a single one as an element, it becomes H2. All right, so balancing this, we've got, we're definitely going to need 2 waters, 1 calcium, and yeah, that's it, 1 of everything else. Okay. All right, last but not least, lead with water. Okay, lead with water. Lead's right here. Will not react with water. Easy peasy. This reaction will not happen. No reaction. There we go. That's how you determine if a single replacement reaction will happen. Now let's talk about double replacement. Okay, double replacement. Again, you're going to have to determine if it happens. It only happens in certain situations. So first off, a double replacement, in order for it to happen, one of the following has to take place. Okay, a precipitate or a solid product. Okay, something that is solid and not soluble in water has to form. Second condition, water forms. You make water, H2O. Third condition, a gas, such as carbon dioxide or some other gas is formed. Okay, so you either make a solid, a liquid, or a gas, and it happens. Okay, this is going to happen. Now, what I'm kind of forgetting here is double replacement reactions. In order to do these, since it's basically 2 ionic compounds, where you've got an ionic compound, they're switching partners, in order for this to actually occur, they both have to be soluble. They both have to be able to dissolve in the water. So they're going to separate into their 2 separate ions before they mix. And then you take the 2 compounds broken apart into its ions. And if the ions meet and they form a solid, or they form water, or they form a gas, then they're going to react and make that solid, make that water, make that gas. Okay? So that causes the reaction to happen. However, if they don't form one of these, okay, those 2 ions meet and they don't form one of these, they're not going to react, so they stay just ions floating, and nothing happens. All right? So here are some reactions that are double replacement. Okay, now all of these are going to involve some sort of ionic compound with a positive and a positive and negative. And again, they have to be aqueous, both of them, so that those ions are broken apart. So we have NH4 ions and S ions floating separately apart in the water. And then we've got lead ions and nitrate ions floating separately in the water, and they're going to mix together. And what they're going to do is they're basically going to swap partners once they're able to break apart. So what I'm going to do is I'm going to swap the negatives, okay? So and see what we create here. So I'm going to swap the negatives. So instead of being NH4 paired with S, I'm going to have NH4 paired with NO3. Okay, now I'm going to do this one. Lead, instead of paired with nitrate, it's going to be lead paired with S. Now I'm going to look up the charges for all of these. Okay, so this is a positive 1, that's a negative 1. This, since it's a negative 1 compared to this, and there are 2 of them, that makes this a positive 2 over here. So this is a positive 2, and then sulfur is a negative 2. So they're both 1 to 1, as I wrote them right here. Now here's what you need to do. Once you know what you're creating, unfortunately with the double replacements, you have to figure out what you're creating before you can determine if it's going to happen. Okay? So once you know what you're creating, we're going to create NH4 paired with NO3. You have to look up and see if this is going to be a solid, a liquid, or a gas. Okay? Now, none of these are water. None of these are a recognizable gas like carbon dioxide, CO2. So maybe one of these is a solid. Okay, now here's how we determine. Remember, this is dissolved in water. Okay, so these might still be dissolved in water, just kind of floating around. So we're going to use these solubility rules. All right, this is sort of a generalized rules for determining if something is soluble, if it dissolves in water. So right here we have compounds which are always soluble if they contain one of these ions. So if it contains group 1 cations, group 1 being the things in the first group or first family of the periodic table, like hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, those sort of things. Okay? They are always soluble. They have absolutely no exceptions to this. They're always going to be aqueous. They're always going to be soluble whenever they have one of these ions as part of the compound, period. Ammonia, same thing, always soluble. Nitrate, same thing, always soluble. Acetate, same thing, always soluble. Hydrogen carbonate or bicarbonate, same thing, always soluble. Chloride ion, if it's a part of it, same thing, always soluble. Perchlorate, always soluble. Halogens like chlorine, bromine, and iodine, okay, they are always soluble with 3 exceptions. There's only 3 exceptions here, so this is where I'm getting some of those exceptions. Silver, mercury, and lead-2. Okay? Mercury 2, by the way. No, mercury 1, I'm sorry. Sulfate ion, always soluble except for 6 exceptions. Silver, calcium, strontium, barium, mercury 2, and lead 2. Right? So if it's paired with anything else, it will be soluble. If it's paired with, say, silver, silver sulfate will be a solid. All right? Anything paired, though, with an ammonium or a nitrate will be aqueous. It will be soluble. Okay, so if I go back to my thing here, this is ammonium and nitrate. Both ammonium and nitrate are always soluble, so they will be dissolved still, no matter what they're paired with, which means this will be aqueous, and we will still have ammonium ions and nitrate ions floating around. They will not react to create this compound. Nothing will happen for this. Okay? So let's take a look now at the lead sulfide, Pb and S. Okay? So these are the things that are always soluble, with a few exceptions. These are the things that are always insoluble, which means they're going to form a solid. Okay, this includes carbonate, phosphate, chromate, hydroxide, sulfide, and oxide. There are a few exceptions where they do dissolve, most of which involve the things here that have no exceptions for being soluble. For example, if I have carbonate, which is always going to form a solid if it's some sort of carbonate, unless it's with the group 1 things or NH4, because group 1 cations and NH4 are always soluble. Okay? So this will basically be soluble if it's, say, sodium carbonate, but anything else besides those few things, and it will be a solid. Okay? Sulfide is one of those. Right? Sulfide will always be a solid with a few exceptions. Okay? Exceptions being sodium, lithium, things like that in group 1. Ammonium, because those are always soluble. Calcium, strontium, and barium. Okay, calcium, strontium, and barium. So if it's with one of these, we will not have a reaction. But if it's not with one of these, we will. It will form a solid because it will not dissolve in water. All right, so if I go back over here, it is with lead. And that is not one of those exceptions. So this will form a solid. It will not dissolve, which means if we have these two things broken apart, floating around in water, and a lead ion and a sulfur ion find each other, they will form PbS. Because that is a solid, it will not be dissolved in the water. Okay, let's try the next one here. So, we've got sodium chloride dissolved in water, lithium nitrate dissolved in water. Okay, we're going to swap partners here. So I'm going to swap the negatives. So we're going to get, instead of sodium paired with the chlorine, sodium pairs with the nitrate. So NaNO3. Okay. Then we have the lithium. Instead of being paired with nitrate, it's going to be paired with the chlorine. So we're going to be left with LiCl. All right, let's check charges here. We've got positive 1, negative 1. Those are the same, so 1 of each. And then we've got positive 1, negative 1, 1 of each. So we're good there. Let's determine if any of these are soluble or insoluble, solid. Neither of them is water, neither of them is a recognizable gas. So go back over here, we got sodium and nitrate. Nitrate, always soluble. Sodium is one of those group 1 cations, always soluble. So sodium nitrate is going to be soluble, which means it will be aqueous. Not going to react there. All right? Lithium chloride. Lithium is a group 1 cation, always soluble. Chloride, one of the halogens, is always soluble except when combined with silver, mercury, or lead, and that is neither of those, so this is also going to be aqueous. So those are still going to be separated, floating around in solution. So we have these broken apart when dissolved, and then these broken apart when dissolved. So none of these ions, when they meet each other, are going to form anything, which means this reaction does not happen. Not a reaction that will happen. Let's try the next one here. So this is H2SO4, sulfuric acid, and NaOH, sodium hydroxide. Both of them dissolved in water. Okay. So what I'm going to do here is, again, swap them. Swap the negatives. So this is going to be H, instead of being paired with SO4, it's going to be H paired with OH. And then the other one, we have Na, instead of being paired with OH, it's going to be Na paired with SO4. I'm going to check my charges here. So hydrogen is positive 1, that's a negative 1, so that's 1 to 1. Sodium is a positive 1, sulfate is a negative 2, so this is going to have to be 2 of the sodiums to cancel out that negative 2 of the sulfate, so it's Na2SO4. Okay? Now, go ahead and look these. Oh, wait. HOH, HOH, also known as H2O. We just made water. So this reaction does happen because with the hydrogen ions and the OH ions floating around, when they find each other, they will make water. So this is a reaction that does happen. Already we know it. It made water, one of those other conditions besides making a solid. Okay? So this reaction does happen. But let's also look up the sodium sulfate here. And if we look that up, sodium's right here. It's always soluble. Okay? Sulfate is down here. It's always soluble, except for these exceptions, which sodium's not one of them. So this is going to be soluble. So this will be aqueous. So this will still have these two floating around in solution, separated, but we will form water. So this reaction does happen. Okay? Okay, next one here. Again, dissolved in water. All right, both of these are soluble. So what we're going to do is swap them. I'm going to swap the negatives again. Carbonate swapped with the chlorine. So we're going to have, instead of sodium carbonate, we're going to have sodium chlorine. So that is Na paired with the Cl. And then magnesium with chlorine, magnesium now with carbonate. So it's going to be MgCO3. Okay. Let's check our charges on these. So sodium is positive 1, this is negative 1. Magnesium is positive 2, carbonate is negative 2, so 1 to 1 and 1 to 1. So those are the correct formulas right there. Now let's see if they're soluble or not, because neither of those are water or a recognizable gas. So I look them up. First one is sodium chloride. Sodium, always soluble. Okay? So that one's aqueous. So no reaction due to that one. Okay? Next one, magnesium carbonate. Okay? So I don't see magnesium anywhere on here, but I do see carbonate, which is always insoluble. Always insoluble, forming a solid, except when paired with group 1s like sodium and lithium. Calcium or magnesium is not one of those. Or ammonia. So it's not one of the exceptions, which means this will be a solid. It will not be dissolved in water. So when a magnesium ion and a carbonate ion find each other, you will get a magnesium carbonate. This reaction does happen. All right? So since it happens, we've got our two products. Don't forget to go back and balance it. So balancing it, we're going to need one of these and one of these, and we're going to make two of these and one of these. And I just realized I forgot to balance these previous two. So this first one that we totally did, I forgot to balance that. We're going to need one of these and one of these, or two of those. One of those. This reaction doesn't happen, so we don't have to balance it. This reaction, we are going to need one of these, two of these. We're going to make two waters and one of these. Okay? I forgot to balance those when we were doing them. Sorry. All right. Last reaction here. KOH, soluble, reacts with calcium nitrate, soluble. Okay? So what are they going to make? Well, here's my negatives. We're going to swap them. So now it's not going to be KOH, it's going to be KNO3. And then the other pairing, we're going to have calcium paired with hydroxide instead of NO3. Okay, let's look at the charges here. So K's charge is +1, nitrate's charge is -1. So that's 1 to 1, so there's the formula for that. Calcium hydroxide, this is +1. No, +2, sorry. Calcium is +2. Hydroxide, though, is -1. So in this case, those don't match. So I'm going to modify the formula here. We're going to have two hydroxides paired with that calcium. All right? So let's see if this happens. Okay? So this is potassium nitrate. Potassium, always soluble. You can also look up nitrate, always soluble. So that one, soluble. It's going to be aqueous. So it's not going to happen due to this one. Okay? Now, calcium hydroxide. Calcium's not on here, but hydroxide is. It's right here. Hydroxide is always a solid. Always a solid, except when combined with these exceptions. So it is always going to be insoluble, a solid, when combined with group 1 cations like lithium, sodium, potassium, things like that, which it started with. Okay, it started with potassium here, so that's why it was soluble there. Or ammonium, calcium, strontium, or barium. It is paired with calcium. That is one of the exceptions, which means that this is not a solid. This is soluble, so it would be aqueous. So this reaction doesn't happen. It doesn't form a solid, water, or a gas. And that is how you determine if a double replacement reaction happens. It has to form a solid or water or a gas, like carbon dioxide.